These talks are in fact part of a series. We video them. They are on our website, and you can find them there. Oops. Let us back up at that URL. And this one will be too, as soon as we've done the video editing process. It will wind up on our website there. So if you miss anything, you'll have an opportunity to do it, review. And yet here you have the advantage of being a live audience, and you can ask questions and all. There will be an Ask Me Anything session at the end of the talk. For now, while I'm doing the talk, please keep your questions devoted to the particular slide. If there's something which is not clear, then that's fine, but more general questions, and I'm sure that you will have some, we can do at length after the talk. A warning, much of what I have to say will be a gross oversimplification. It is intended for an intuitive understanding for a non-specialist audience. If you are a specialist and you see something which is obviously ridiculously oversimplified, the answer is yes, it is. And please bear with it. During the Ask Me Anything, I will be more than happy to get down into the dirty nitty-gritty of anything you'd like. But be aware that what I'm telling you, the reality is, in fact, more complicated. We try not to oversimplify, but sometimes it's necessary. The purpose of the talk, most of our talks in this series are about the MIL architecture. The MIL is a general purpose CPU family offering substantial, like 10x, performance, power, area advantages over existing architectures. We've been doing it for a decade, and we still have more to go. But one of the things we have done is we've published the technology essentially as fast as we filed the patents on them, and their descriptions of what is novel about the machine are available on the site. This talk, however, is not going to be talking about the latest, newest MIL whiz-bang. Instead, it's going to be talking about how the general ordinary things about the MIL architecture impact perfectly ordinary simple code and what constitutes good code in light of the architecture that it's going to be running on. For an example, we'll be using the classic switch statement. Nearly every language has one. They differ in syntax, but basically it's a multi-way branch. This is a known pain if you are at all in the compiler business. Getting decent code and decent performance out of a switch is difficult and annoying. Of course, the question is, does that make any difference? After all, switches are not that common. But in some cases, it does make a difference. Lexers, where you're switching on the character in order to parse, to lex and isolate tokens, is an example because lexers, unless you're doing heavy-duty optimization, the lexer dominates the compile time or a compiler because lexer is doing everything a character at a time. But once the lexer is done, everything is being done a token at a time, and there's many, many fewer tokens than there are characters. And consequently, the lexer actually is a performance critical, that is compile time performance, not generated code performance, compile time performance critical part of a compiler. Bytecode interpreters, similarly. Network dispatch, where you get a few bits coming in off a network packet and have to decide what to do about it. These are places where actual switch overhead can be significant. But as a practical matter, in most cases, it doesn't really matter all that much. But it makes for a good test case, and in the words of Robert Burns, many a mickle makes a muckle. A little bit here and a little bit there has a tendency to add up after a while, and it is interesting how the little bits get influenced by the architecture that you're running on. Why pick switches as a topic? Frankly, happenstance. There was a question asked on CompArch, and there is a Yes, there still are news groups. This is a mystery to many people, but they do in fact exist, and CompArch contains a collection of fossils, including myself, who talk about historical architectures of various things, and we've talked about the mill at some length. And one of the questions came up was, does the mill have any special operations designed to support switches? And the answer is no, it doesn't, and they explained why it doesn't. And then this in turn prompted a question on the mill forum, which is on our website. That is the URL for the mill forum. And people come in and talk about various aspects of the architecture. And evidently this user had seen the article in CompArch and said, well, I read the answer, but I didn't understand it. And here's an example, please explain. So he gave us a piece of code, which promptly crashed the compiler. The tool chain is, especially at the time when this was being done, the tool chain is pre-alpha. It is pre-alpha, we'll leave it at that. But we fixed the compiler, and the result was pretty good code, and it made a pretty nice example of showing exactly what happens in mill code and what the then current state of the compiler was producing. So we posted the resulting machine code to the forum for his example. This was his example. Okay. Simple function, does nothing but a switch, returns a value, different values based on what the cases are. Note that there's a function call in the middle of that thing. And there's a wide distribution of case values. All of these tend to be annoying things in the processing of cases in compilers, in the processing of switches in compilers. And our thanks to Goldbug, who gave us the example. Well, this wound up being a good representative example for us to look at. And I need to define the terminology that I'll be using. The value you use to decide where you're going to go is called the selector. Where you do go, the different various code addresses are called the targets. The value that determines which target you're going to go to is the case. And when you have a contiguous sequence of cases, all of which go to the same target, that's called a case run. So I'll be using these terms throughout just to, if you're not a compiler person, the terms may be unfamiliar, so I'm defining them. Now there's a bunch of ways to implement a switch. The classic and simplest way is you simply do an if test for each of the cases. 1, 2, 3, 4, down you go. So that gives you a linear chain. In the case of our example, we would first test to see if x was 0 and we go somewhere. And if that's not, we check to see if x is 2 and then we go to its target. And well, you know where this is going, you get all of them. There is one test for each non-default case. And there is, you will, on the average, because it's just a chain of ifs, you will wind up doing half of the tests. If you have profile information, you optimize, you can put the common targets at the front to be tested early, and this will reduce the number of steps you have to go through on the average, if you have profile information. And this actually gives surprisingly good code if there are only a few cases widely dispersed in the defaults. The very best case is when there's only one case, and then it turns into an if. An alternative implementation, you do a binary tree of ifs. Here you partition the case space into a sequence of runs, sorted. And so if x is less than 7, we go down and check, well, is x less than 101? And if not, we go over to the default case on the end. And if it is, we go down and check again, check for another couple. And well, you know where this is going. So it's just a classic binary search. The compiler generates all the necessary branches and so forth to do it. However, here, instead of having one entry per case, you have one entry per case run to separate adjacent runs. So if the distribution of cases is we do all the alphabetics together and they all go to the same way, well, instead of doing a case of ifs, you've got 26 tests. Here you're going to only have one or one on each side, so as to pull all of the alphabetic characters, for example, in one test. So which of these two has advantages depends on the distribution of cases. On the average, you're going to have a log n. It's a classic binary search. And here's an exercise for you all. When is n over 2, in the cascaded if, a better deal than log n? And if you think about it a little bit and how these things work, in fact, sometimes it is better for certain values. Left as an exercise. The classic implementation of switches is a jump table. There will be a table of addresses, and the first thing you have to do is to see whether you are in bounds on the table. So are we less than 0, or are we greater than 100, because this is the range of our available cases, and if we're outside either of these ranges, then we are going to go to the default case, and otherwise we are going to index into a table of jump addresses and load it and jump to it. Whether we load and jump, or on some architectures actually directly support the ability to jump through a memory location, that depends on the microarchitecture of your machine, which one you're going to use. Most of the talk here, I'm assuming that you're something which is vaguely RISC-like, so that you're going to load and then jump, but the details wind up being relatively minor for something like this. You do wind up having an entry in the table for every case once you've trimmed off the bounds. The fact that cases come in runs are irrelevant here, and you do have to have an entry for all of the default values in between the cases, which is not true for the cascaded ifs. Typically, you wind up having 2 tests plus a indirect jump. Now, when you do use a switch table, you wind up having to address one question, which is where are you going to put the table? One possibility, because the table is constant, is you can put it right in the code itself. And that was, in fact, the traditional way of doing it up until about the 1980s or thereabouts. It's a classic Fortran approach. Or alternatively, you can put the table in the data space. These have different trade-offs that I'll touch later on. So these different implementation choices, well, it looks like it ought to be easy. Well, it's not. It's annoying. The real problem is that switches are megamorphic. Megamorphic is a term from one of our science advisors, Cliff Click, the guy who did Hotspot. And what he means by a megamorphic point is a point in which everything goes in every which direction and you cannot anticipate where it's going to go. Everything changes continuously. So it's megamorphic. The paths through a switch typically do not follow a coherent pattern. They're continually changing back and forth. Think of Alexa. Well, you do a few alphabetics and then a numeric and then white space and then a right angle bracket. I mean, it's the path through the switch is changing continuously. So consequently, it is rare to go always in the same direction. A modern branch predictor keeps the history of what you were doing before you arrived at a particular jump. And they're quite good, but it only applies if, in fact, where you're going to go this time is in some way correlated with where you used to go before. And a characteristic of switches is, in fact, is not well correlated. You're as likely to wind up in Chicago as you are to wind up in Atlanta, and you're not flying Delta Airlines, you're doing a compiler. So as a result, if you graph this and think of this as being a graph of the relative frequency of taking a particular target as across many, many uses of the switch, Indeed, you'll find situations in which there's, for a particular switch, where one case is the one that's taken overwhelmingly often and everything else is minor. That does happen, but in the wild, it's rare. Switches rarely behave this way. If they do, they're wonderful, but the compiler has to deal with ones in which the frequency of the different cases is relatively uniform and none dominate. Now, when you do have one of these, what people will often do is that they'll recognize this as a special case. They know it's going to go down the value 5 nearly every time, and they'll special case this by writing a if test for the popular branch in front, and then let the case mop up all the remaining values. Well, yes, you can do that, but there's still a multi-way branch that you've now split into two parts. So what you've actually done is you've taken your multi-way branch and you've hand compiled it. Instead of having the compiler be annoyed or the compiler writer being annoyed, it's you that's being annoyed and having to discover that this in fact was your distribution and it mattered to you, so you had to rewrite it. Now, this talk is about the impact of architecture on switches and on the code generation for switches. It's not about how best to write one. So I'm not going to go into, oh, you ought to write an if in front or anything like that. I'm basically going to be showing you for a machine that's different than the kinds of machines that you ordinarily use, what is the impact on the code that you will get and the quality and the performance you'll get out of it. Because everything you write, especially if you're writing system programming, is impacted by the architecture that you're running on. So, they're megamorphic. There's a wide distribution of taken paths. The modal, the most popular path, tends to have a relatively low probability because it's sharing the probabilities of many, many other paths. And the distribution of the different cases tends to look like something like this. This is this kind of thing that the compiler has to deal with. There will always be a few paths which are almost never taken and can be essentially ignored in the analysis, but the relatively popular paths do tend to get in each other's way. Your predictor, branch predictor, will tend to guess that you're going to follow the modal path, the most popular one, every time. Except that you see that's in fact going to be a relatively small percentage of the cases. And so consequently, unless that modal path is in fact taken 90% or better of the time for a given history, then you are in mispredict hell. To a first approximation, for interesting switches, they will miss every time. Misprediction is not cheap. Now, going to one particular implementation, the implementation using jump tables. This comes from the prior slide. The steps are involved. You first have to test low and you have to test high. Those tests must be done before you go and load the entry from the branch table, because otherwise the guy may have given you an index which in fact will cause the load to be out of your address range and you just crashed. And this is a form of exploit which is in fact been used in the wild. It causes the program to load a value that thought it was loading out of a jump table, instead to load a value out of the boonies that happened to have a value that was of interest. So you have to check the bounds first, but those checks nearly always pass, and so the branch predictor will make them be relatively cheap. Then you have to load the address, and then you jump. That jump will mispredict. Now, you might think this is all to it. Well, okay, fine, I got one mispredict, and the load is not all that expensive, and no big deal. Except that that's not all that's involved. In between the load address and the jump, the hardware is doing some more stuff. In particular, it has to reference the translation to look-aside buffer in order to find out where your jump table actually is. And that can miss. And that can send the TLB and translation tables into a tail-chasing fit if this is a location that you're not normally touching. Then after you have the TLB that does the translation for you, then you have to get the value out of the D1. If it's in the D1, it may actually be over in DRAM. And that is not cheap. Then you jump and you mispredict. The result is this can take a long time. This is the reason why, in fact, jump tables are, in modern times, unless you have a very large, very dense, with few runs, distribution of cases, jump tables tend to be less performant than the other forms involving using chain of ifs. And you hope that the code quality guidance functions inside the compiler will pick a encoding strategy which reflects this. They don't all do. Now you can get rid of some of this problem. If you put the jump table in the code space, well, the code, you just executed this jump, so you know that it's in the TLB because the TLB just looked at it. So the table's read-only. It's like code. If you put it immediately after the jump operation, which you can, there will not be a TLB miss. Similarly, that code is in the instruction cache. You just executed it, so there won't be an instruction cache miss either. So we now have the jump, and we will still have the mispredict. And indeed, the test low, test high, load, and go in many older architectures was turned into a special check operation, and you'll find some rather odd special operations in machines dating from the 60s and 70s whose purpose is to implement this exactly as it is. So why not put it there? Well, it does work if your machine doesn't have a cache, and if the data paths in the machine are less than or equal to the size of an address. If you are a 32-bit machine and your data path is 32 bits wide, and your path to memory is 32 bits wide, then this will actually work quite well, which is why it was used in the old machines. These days, however, it's no longer 1980, folks, and today's machines have caches which fill a whole cache line at a time, not 32 or 64 bits. And the instruction fetch going from the cache into the decoders are at least 16 bytes and frequently bigger than that. So they're grabbing big hunks which are naturally aligned hunks and feeding them into the instruction decoders. There is no pick a byte out of the instruction space. That would require data extraction shifters, and those are just physically not present because they would be in the way of the critical path for instruction decode, and you do not want anything in the critical path for instruction decode. So you got to have the shifter if I'm going to pull out these 4 bytes out of this array of bytes, and the way you do that is you take the bits up and you shove it in to select them, and that's basically a shifter. And where do you put it? And the answer is you don't. Instead, the microcode of the architecture, which claims that it's reading a value out of the instructions, isn't. It takes the whole cache line, ships it over to the data side. The data side already has all the shifters, so you can pick up an integer or a double or what have you out of the data cache. The data side grabs the stuff up and presents you with the now loaded value, pretending, oh yes, I got this from the instruction cache, it lying through its teeth, and will in due course give you a value that you can jump through. This is actually a major problem in a modern machine because the instruction caches and the data caches tend to be not well coherent, and there has to be special hardware to keep everything so that you have got the right value in the right place in the right cache in order to be able to pretend that you got it from the instruction cache. Modern machines do not have Modern, I do not mean x86, that's an old machine. A modern architecture will not have any way that you can pull a data value out of the instruction stream. So, the next factor to be concerned about if you are dealing with switches is branch prediction. Here's my chain of ifs from before. Each one of these branches, is it x equal to 0? Is x equal to 2? It's going to have a branch predictor, which will be a history predictor that knows what you did the last time you came through here with a similar history. And it will say, is this branch going to be taken or not taken, false or true? Each one of them will have an entry in the predictor tables. And essentially, the first test is testing, is x equal to 0 more likely than all the other possibilities put together? If it is, then it'll predict true, it'll predict taken. But as a practical matter, remember the cases tend to be about even in frequency. The first one is not going to be more likely than all the others put together. So the branch predictor will say, no, you're not going to take it. And in fact, the same will continue all the way down until we finally get to one in which it is more likely than everybody else you haven't looked at. The predictor will say, yes, take this. That's the first taken prediction. And once you have one of those, you can indeed have for others. There may be more down here or more likely than everybody after them. So this is what the situation you're looking at as you attempt to go down the chain of ifs, with the branch predictor guiding you as to whether you ought to go this way or got to go that way. Let's assume for the moment that an actual case, our value of our selector was 5. And so the x equal 5 is the one that we ought to be, is the case, and its target is where we ought to be going. We will chain down the top, and when we get to the x equal 5, we have already long since gone down to the target that belongs to x equal to 5, fallen through to the x equals 6 and so forth. And we discover that, oops, we did in fact take the target for x equal 5, and we have to throw away everything that we've already done going down the chain of ifs. We have to toss the pipeline, we have to toss the in-flights, the reorder buffers get thrown away, we have to restore the machine state, we have to potentially load up new cache lines in order to get the decode restarted, and in typical machines, you're looking at 15 or 20 cycles worth of delay. It is not cheap. That cost of that search chain, in contrast, is at most 1 cycle per test. Actually, you can do better than that in hardware. So the cost of chaining down it is cheap compared to the miss. To a first approximation, you are going to miss every time. Now, there's 2 kinds of misses. This is an early miss, where the miss precedes the prediction. We were expecting to keep on going, and we decided that when we finally got it and evaluated the branch that we're not keeping on going, we're going somewhere. The good news is that once we're out of this chain, we're only going to have that one miss. That's it. We're now in the correct place. That's good news. Now, however, that's not the only possibility. Again, we have the branch predictor's predictions for each one of the tests. And let's say that because that is the first case that the predictor thought that we would in fact take, and so we predict x equals 5, and later on there will be more predictions for the rest of them, and the second guess is x equals 6, and let's say that in fact actually x equals 7. Well, obviously when we get to 5, which said that, oh, go off over there, it's going to be 5, we will mispredict because we didn't go over there. Instead, we kept going down the chain. When we reset ourselves, restart everything, go down and take a look at 6, and 6 said we were going to exit 2. No, we missed again because we have to keep on going down the chain. So this is 15 to 20 cycles for each miss as we go chaining down. And indeed, it's entirely possible that the actual that we hit might have been predicted not taken. So when we get to that, we're going to miss 2. So if this is late miss, where the predictions precede the miss, and you can potentially have many misses as you work yourself down the chain. The bad news is many misses. Now, to summarize, you've got a linear chain of ifs, average half of them. Miss if you're lucky. Log n tests here for the binary tree. And here's another exercise for you to do at home. For a given distribution of selectors, what is the expected miss rate as you work your way down? Naively, you'd think, well, you'll miss each one 50-50. I mean, it's a binary search. It's going to go that way, it's going to go that way. Work out the exercise. You'll find it interesting. As a first approximation, yes, you'll miss at every other level, but that depends greatly on the distribution you're looking at. And in short, yuck. This is why switches are annoying. Well, of course, this is a mill talk, and so we talk about the mill. What does the mill bring to the switch party? To begin with, the mill is a wide issue, statically scheduled, exposed pipeline machine. It is loosely related to VLIWs and the EPIC machine architecture that was used for the Itanium. It is not a VLIW, but it does share with both the VLIW and the Itanium the fact that it can issue many operations simultaneously. It's a family, and the number of operations it can issue simultaneously depends on which family member you have. These range from 5 operations every cycle up to more than 30 operations every cycle. These are independent operations. It is MIMD. This is not SIMD where you're doing the same thing on a vector. These are all independent, different things that you're dealing with. So its width is extreme compared to a conventional machine. Conventional machines typically max out at a sustain rate of 4 ops. If you pick exactly the right ops, you get 4 ops every cycle. This is typical of modern machines. We run much higher than that. Phasing is I'll touch on later, but MIL does not issue single operations. Instead, it issues short data flows consisting of 3 operations which feed into each other. This makes a big difference in the performance quality, as you'll see. We do exit prediction rather than branch prediction. This also I'll explore. And it has a very cheap mispredict, where, as I said, typical is 15 or 20 cycles to recover everything. On a mill, a mispredict is 5 cycles, plus whatever cache or DRAM you have to do if when you were supposed to go, the code was or not, in fact, around. We still got to go and get the code just like anybody else. And multi-way branching is supported. You can have multiple branches in a single instruction, multiple branch operations going to different places for different reasons in a single instruction. And there's a mechanism to decide if more than one of them say, I want to go somewhere, to decide which one gets to win. It's called first winner rule. The family is driven by specification. All of this software has been in place for several years now. Each family member has a common architecture and a shared binary interface which uses an abstract architecture and abstract microarchitecture so that code is portable from family member to family member. The abstract is standard across all mills, but the individual family members are identified by a specification that determines what concrete operations are present in that particular family member and how many of them you get. A designer describes a particular family member by writing a specification. That's typically a couple of pages of code, and that entire process is specification-driven. Then Once we have the specification in hand, our existing software then takes the specification, cranks through it, determines what the bit level instruction set is, and constructs tools such as compilers, debuggers, and even generates the Verilog that drives the creation of the hardware. For the purposes of this talk, I'm going to be using one family member as an example. It's a mid-range member. It's called Silver. It's a little bit of what it's populated with, so you can get a sense. There's a pretty standard 32K top-level data cache. There are two 1K microcaches on the instruction side that why we have them you can ask questions about if you want, or it's all on our website where we explain all of this in other talks. And there's two 64K top-level instruction caches, and why there are two and not one is also something that you can explore at your leisure on the videos of other talks and the slides, all of which are on the site. In addition, it's populated with a bunch of functional units. There are 4 ALUs, 2 floating point units, 3 different branch units, 4 load store units, and a bunch of miscellany that doesn't really matter here. You do not get all of these at once because some of these share resources. So you can have 4 integer operations, or 2 integer and 2 floating point, or 3 integer and 1 floating point, or so forth, because they are sharing certain common resources. So you can't get all of these at once, but the population that you can get all at once, it can sustain an issue rate of 17 operations per cycle on a sustained basis for a random mix of operations, assuming that you're not trying to do 5 ALU ops in one cycle, because there's only 4 ALUs, we can't do that, but you can push that onto something else. A reasonable way to think about a Silver is it's a 17-wide superscalar. And yes, that is a mid-range for the Mill family. Back to our example. Remember the example? What we get out of the front end and middle end, which are the standard LLVM toolchain, Clang front end and LLVM, is this stuff, which we call genAsm. And this is the textual form. It comes in a binary form too. And this is almost identical to the internal code, the IR code that Clang uses, that LLVM uses internally, and I'll explain a little bit about what it means, but this is in fact the result that LLVM produces for our little test case. Now, ours is almost unchanged. We have tried to minimize the amount of ruckus that we have to do within the Clang and LLVM. Backends for other architectures, ARM, x86, whatever, exist, and they have to eat something like this and turn it into code for their machine. We have such a backend that we have produced ourselves, and you'll see the output code coming from that in just a moment. The things that are being circled, con, call, br, these are mill operations. Con means give me a literal constant, in this case the literal constant 1. Call means do a function call. Br is branch. And so these are just operation names and correspond in most cases quite closely to the machine operations after code generation. Each one of those has a set of arguments, and what the arguments are and what they mean don't matter here, but essentially what we have to process are operations and arguments and turn them into machine instructions and their arguments. The code contains basic blocks. Each basic block has a label, and the basic block continues until we get to the next label. And the labels can be referenced by being preceded by a $sign. So label $1 is being placed there at the top, circled value on the left, and it's being referenced there on the FIOP in 3 lines below it where you see $1 being referenced. That's a reference, that's a code reference. LOVM is a static single assignment architecture compiler. That means that no values are ever changed. New values are created, but once a value is created, it's never changed. Static single assignment is a very fundamental concept inside compilers. Wikipedia has an excellent article on static single assignment. If you're unfamiliar with this, I would strongly recommend reading that article. You'll give you a lot of insight into exactly what's going on inside your compilers. Pretty much all compilers these days use this as an approach. Old compilers, if you knew what old compilers had to do, you'd understand why it was changed. The values which are produced by an operation are indicated by a percent sign plus a number. So that %2, which is there, is the value being produced by the conop. So it is the literal value 4. And the other places where we have a percent followed by a number, those which is not followed by an equal sign, this is a place where this value is being referenced. Note that the equal sign does not mean assignment to a variable. Those are not variables. It's a let type operation. It is defined and that's it, and you cannot change it thereafter. That's our switch. That's the selector. Those are the cases that we had. And those are the targets we're supposed to go to with the corresponding cases. This is what the Clang and LLVM have done when they parsed the switch that contained in our code, and this is what they give us to tell the code generator, this is what you got to work with and what you have to produce code for. Now we're a wide issue machine. That means we can put out a whole bunch of operations at once. So each instruction actually contains a bunch of different operations. Those operations are encoded in positions in the instruction called slots, and those slots corresponding to pipelines in the execution engine inside the machine. So when a operation is in a slot N, it will wind up being routed to pipeline N during execution. For execution. There may be multiple different kinds of functional units in each slot, and you can only use one of them, which is why in Silver, where there's a slot which is both an ALU and an FPU, you can use one or the other, but not both. Now here's the generated code. This code was produced by our perfectly ordinary regular compiler at the time when these slides were being created fairly recently. So what you're looking at is a work in progress. I told you the tool chain is pre-alpha. You can expect that if you run that same code in 6 months, you may find differences in the code that's being produced, but this is what you're getting today. This is the generated code of the first instruction of function bar. You'll note that it's got a whole bunch of operations, but it's got a function entry point. Oh, this is bar. This is where I come in. There has a function argument. That was X that we had. And that, guess what, is percent sign 0, so you can reference X. These things are the operations. These things are the results of the operations. And the semicolon at the end says it's the end of the instruction. This is assembly language for a mill. A minor note here. Mill is somewhat CISC. So, for example, operations which require an idiom or complex setup code on a typical RISC are one instruction on a mill, and particularly call and return are one instruction with lots of different arguments depending on what you needed. And because they're only one instruction, they can be predicated. You can hang a bool on it saying whether to do it or not. And in this case, the RENTR down at the bottom, that is return if true. So if the bool is true, then we do a return. If the bool is not, we don't do a return, and it saves us having to jump around a return operation. So this is the first instruction of bar, and this is what they mean. RD is what we call a popcon. It's a way of a very compact encoding of giving you a small literal constant. So we drop the constant 1 and we call it %1. And we do again for 4 and call it %2. Now we've got a regular operation, EQL, naturally enough it's an equal, and it drops a Boolean value. We do not have condition codes. It does not set condition codes. It actually drops a genuine 0 or 1, and that's a Boolean value. And we'll call it %7. And another bool, and another bool. Note that these 3 are using 3 different ALU operations, but we got 4 ALUs. We got plenty of room. And then the return true, it tests the predicate. So in this case, if %7, and if you look up above, %7 is the bool coming from x equals 0. Then return, and the value to return is %1. If you look up above, %1 was the guy who dropped the literal constant 1. So what that operation is saying is if x was equal to 0, return the value 1. That's what the operation does. And similarly for the next 2 return trues, testing 2 other cases. This is the first instruction. But if you've been following along here, you may have noticed something rather odd. That return is using a %7 that hadn't been created yet at the point when we started this instruction, because the equal hasn't been done yet. It hasn't yet had a chance to drop its result. That's rather odd. It's kind of like an adder being able to add its own result, and that doesn't really work in hardware because we don't have time travel in hardware yet. So how does it work? Well, funny thing I'm going to tell you. A mill instruction is not a collection of operations that all execute at once. That's called a VLIW. Mill is not a VLIW. Instead, it's a collection of 3 operation data flows that are phased issued staggered over 3 cycles. Not everything going out all at once, but dump, a dump, a dump. Only 1 instruction, but spread over 3 cycles. So if we use these pink lines to indicate that this is a cycle boundary, what's really happening is it's not all done in the first cycle. Instead, all the things which take both an input and produce an output are done in the second cycle. What's done in the first cycle? Well, the reads. Those take no input. They only have outputs. They're done first. The following cycle, the things that take inputs and produce outputs. And then the last cycle contains the things which take inputs and don't produce outputs. So, though the instruction contains a group of operations, it's actually containing data flows which are staggered over 3, and because they are over 3, we can move %7 from the middle column into the input of the return in the 3rd column as if they were in different instructions. All clear?
Actually, a question on that. You're saying it does that like by definition, not in this specific example, like always inputs, middle outputs.
Which phase a particular operation operates in is part of the specification.
Okay.
And for various encoding and other reasons, we do break them down. Do you have any inputs? Do you have any outputs? Do you have both? Because this makes the chaining the data in between cleanly.
So things with both inputs and outputs cannot change together. You only have 1 second.
It appears that as you read it, that you're passing things inside the instruction. It's actually being staggered over 3 cycles. But what's interesting is that the data flows of multiple instructions overlap. So this is the whole program, all of bar. There's the first instruction we just saw. There's the second instruction. There's the third instruction. And that's it. That's all there is. Now, 3 instructions. maximum of 3 cycles. And of course, if any of these return trues happen to be hit, you'll be out even earlier than that. If you add up all of that and figure out what the ILP is, you have an ILP of 8. The conventional wisdom is you'll get an ILP of 2 in ordinary code on ordinary machines. We do a bit better than that. Now I'm going to color code the instructions to make it easier to understand. So the first instruction is in yellow, the second is in orange, and the third in blue. And we'll give you a bunch of cycle boundaries. So the yellow goes in those 3 cycles. But remember, the consecutive instructions overlap. The orange has got no pure sources, but the remaining some in and some out, and only in go stepped over 1 from the previous instruction. And the blue winds up like that. So that at any given time, the machine is executing the first phase of one instruction, the second phase of another instruction, and the third phase of still another instruction simultaneously. Okay? Yes. But I've been saying this is 3 cycles. But it sure looks like 5 cycles. But no, it's not 5 cycles. The end cycles, remember this is a function, the end cycles overlap with the corresponding phases and cycles of the caller. So that first cycle, you're actually in the caller, and the fact that we are executing 2 operations is because we're executing down the predicted path, and that code is being executed while you're still in the caller. Then we're in bar, and bang, 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 we have 3 cycles. And then the last part, again, we have exited, and the cleanup to verify that we should have gotten where we should have, which is what these returns are doing, is being done overlapped with the execution of where we went when we returned. So there really is only 3 cycles there, even though it's spread over 5 cycles. Some of that is shared with your caller, both coming in and going out. If you look carefully at that data flow schedule, and if you understand what's going on inside an out-of-order machine, which does dynamic scheduling, this scheduling looks almost identical to what the hardware on a Xeon high-end x86, for example, is going to do the same thing. It is going to accumulate the operations, and as soon as the data is ready for it to go, and the execution resources are available, they'll fire the operation, and their goal is to keep data flowing without any pauses. So the result of this goes to that, the result of that goes to that, the result of that goes to that. Well, if you look closely, this is exactly what we got. The result of this goes to that, the result of that goes to that, and the result of that goes to that. And mill schedules wind up being, though they're statically scheduled by the compiler, they wind up being essentially identical delta minor variations of what the operations do as what is done in hardware on an out-of-order machine. Done in hardware at incredible expense in an out-of-order machine. Power expense, area expense, and what have you. However, that's only if everything works fine, but there's always mispredicts. Remember, we always do mispredict, and this code, though it's implemented in terms of the return true operation, it's semantically, it's basically our chain of ifs. There are 7 return trues. Are there 7 chances to miss? Well, there would be if it was a genuine chain of ifs with branch prediction, but it's not. That's because we don't do branch prediction. We have one prediction to rule them all, and the way we do that is because code is organized in extended basic blocks. Code is grouped into single entry, multiple exit sequences of instructions. So if this is an EBB, your branch can only enter at the top of the EBB. It is not possible to jump into the middle. EBBs are chained by the branch target addresses. So you don't have to predict each branch. That's because you're only going to leave the EBB by one of these branches. You can't jump into the middle of it. You're always going to come into the top. So, and one of these guys is going to get you out of here. So rather than saying taken or not taken to every branch, we simply tell you which one you're going to leave with. That is, we predict exits. We do not predict branches. So there, for each EBB, there is one, you're going to leave it here for each history pattern that your predictor is using. We predict exits, not branches. If control enters there, and we predict that control will exit there, that's all there is for the prediction. Now, we just did branch prediction with, there is a bunch of possibilities, and if the actual is down there, you're going to, all the predicted taken cases up to the actual one will miss, and the selected target will miss too if it was predicted not taken. If you have exit prediction, there's only one prediction that says we are going to leave there. If it turns out that we leave earlier, remember, they don't predict lousy for us just as well as they predict lousy for a branch predictor, then we will have an early miss. The miss occurs before it's predicted. We will have a miss penalty, same as branch prediction, just anybody else who's doing an early miss. If, on the other hand, we have a late miss, that is, we predict ahead of where the actual is, then we will miss once at the predicted point because we'll have been predicted and sent ourselves down to a target that we're in fact not going to. We have to reset ourselves, get back on the chain, and then we will miss again when we get to the real one. However, when there's a uniform case distribution, there's no obvious winner. That is, the predictor can say, oh, this EBB, there's just no telling. It's going to leave anywhere we don't know. And it will throw up its hands and simply say, do the whole thing. That is, it will predict that it will exit at the bottom. And that means that obviously, if we exit before the bottom, that we will miss, but we only have one miss. Now, architects are like grandparents. They love to brag about the baby. One of the things which having a exposed pipeline machine offers immense advantages in power and area, and having a wide machine offers immense advantages in the number of things you can do for instruction parallelism. But traditionally, it has been thought that out-of-order machines made up for that disadvantage because they were able to get better overlap and better instruction parallelism by doing dynamic scheduling. Recent research, and there's a citation here of a paper from Aspos in 2013, which is an excellent paper, incidentally, I recommend it to you, shows that in fact there's two different causes for the advantage that an out-of-order machine has. One of these is that the out-of-order machine is free of a number of hazards because it uses renames. It never has to deal with the fact that two different instructions are using the same register and are colliding with each other. And so there are, in a statically scheduled, you have situations in which you have too few registers and these hazards prevent you getting a good schedule. And at a high-end out-of-order machine with hundreds of rename registers does not get collisions. And so that you can get a much better schedule. And there's similar other ways where dealing with operations which may fault and so forth, where the dynamic scheduling can do a much better job of scheduling than a traditional in-order instruction set. However, that is 88% of the total advantage. Only 12% is the ability to fill in and do useful things because you just missed in the cache and you're waiting for the data to come from DRAM. Well, a statically scheduled can never deal with that 12%. We have other ways of getting at that 12%. But as a matter of practice, with the scheduling methods that I just showed you, we eat that 88% too. We effectively do not have any of the hazards that a conventional in-order machine has, and we achieve the same that an out-of-order machine will get. We have immunity to hazards for a variety of reasons. Ask me or go to the website. All of it's explained. And when we're all done, we can exploit the full width of the machine. We're not limited to the 4 cycles. The reason why they don't do more than 4 instructions is because all of the rename and out-order machinery is n squared, and you simply cannot build a bigger machine to do that. So, in other words, if you had a 17 wide out-of-order machine, you can probably keep up with a mid-range machine. Probably. Until it melts. End of brag. If you want more, documentation is there. We do send out technical announcements. This is not marketing material, but technical announcements such as future talks, among other things. You can get on the mailing list. We are continually looking for people who would like to join the mill team. Feel free to join us. And now, the floor is yours. Ask me anything you want to know.
So how do you deal with switches with hundreds of cases?
The actual algorithm inside first breaks it up into runs, sorts those, and chooses one of 3 different approaches based on how dense they are and how big they are. If it finds a sufficiently large run-free region in the run space, it will in fact use a jump table. What constitutes sufficiently large is member dependent, and there's a figure of merit calculation inside that guides it. Compilers are full of figure of merit calculations. For everything else, if there's lots and lots of individual cases and runs, we will do a top level binary for a couple of levels down to where we get to something that is a practical sequence of ifs. You have to have a pretty huge case. The switch inside Yak or some other compiler where you can have thousands or even tens of thousands of cases. This is a place where, yeah, you'll have a couple of top level levels of binary before dropping into the linear search, and there'll be regions even in the middle of that where there'll be a jump table, a smaller jump table, not for the whole thing. That's what actually goes on inside our compiler. None of that is applied here. This is much too small an example to see any of that. Don't have to restrict yourself to this presentation. If you're interested in anything, feel free. Yes?
Then what are the ones that they should watch? If they couldn't watch them. The order is deliberate. I would start at the top and work down until you can't do it anymore. I mean, they build on each other. They were done at a variety of venues at Stanford, IEEE, Google, a variety of places, but they each address a particular architectural design issue. If you're interested in what is really going on inside the CPUs you use, I realize that you're interested in C++, but guys, underneath you there's a chip.
Some of us pay attention to that.
Some of us do pay attention to that. I've long felt that, in fact, it is a good educational ploy that everybody in school should have to write programs in hand assembly language. You need to know what the machine really does.
There's also a memory bus, and that's another thing people have to learn about.
Yes. Other questions?
You said that you had minimal changes to Clang. I was wondering, what they were.
Well,
There are some intrinsics that we needed to add in order to access portions of the machine. We needed to get out information which is not normally available to the back ends, having to do with inter-operation dependencies which are dependent through memory as opposed to dependent through values. And so there is an ordering oracle that gets spit out. All of that information is available inside the Clang LLVM tool, but it's not normally placed in the standard IR representation that they use. Instead, you would get at it through a function call, but we need to spit it out because the backend needs it. But there's been relatively little actual changes. We are anticipating that there will be some changes coming up. There are some things that LLVM and Clang do that make assumptions that the world is, in fact, it runs C on an x86. And in fact, the world does not just run C on an x86. It does a whole lot of other things. But the internals make it rash assumptions that are true for C on an x86, but not true for other languages and other targets. One of the most glaring things for us is that our pointers are not integers. They have meta information embedded in them. And two pointers can be equal even though they're not bitwise equal. And this is a real problem because Clang has thrown away the value that the idea that something was a pointer, and thereafter you will get integer integer operations on this as if every pointer was a 64-bit integer. It is not for us, and this is a one that we are going to have to be doing some fairly major surgery on in order to correct. There are other cases. If you're interested in the details, I'd be more than happy to bitch and moan about it.
That's actually very close to what I was going to ask, which is, are you tracking the most recent versions of Clang with your modifications?
We had, I'm not involved on that. Two of our guys in Europe are our sort of Clang experts. The question is, are we tracking current developments in Clang and LLVM? We, of course, do track it. Our base compiler is not the bleeding edge Clang and LLVM. It's the most recent stable release that we use. But the people that are definitely aware of what's going on in there, and at a certain point we're going to have to be starting to upstream stuff, but we have not actually begun doing any significant upstreaming. The question was, there had been posts about an FPGA implementation and basically what's the status. We are a bootstrap company. And this is why we have been at this for quite as long as we have been. On the other hand, we haven't fallen on our face yet. The FPGA is, in fact, the next major step. The step coming up to this point was essentially getting the compiler up to being vaguely usable. And the next step is a proof of principle on the Verilog side, and the way to do that without paying for mass sets in order to get chips is we'll produce an FPGA. For us to do that will be another financing round. We've been through one financing round and we're about to launch another one. If you have anybody with 8.5 mil or thereabouts who would be interested in this, especially if they happen to be somebody who has expertise in putting something in FPGA, we would love to talk to them. But the financing round is in process, and the money for the first round was earmarked for patents. At this point, I think we've got something like 9 patents issued, and another 20-odd in process at various points in the U.S. Patent Office. And this upcoming round is earmarked for the FPGA implementation. The round after that, probably around 25 million, is to get something with pins on the bottom on a socket on a board. Now, if you were at all familiar with going from a hardware that runs in software simulation, we've been running in sim for a while, to FPGA, to chip, you know that this is not a fast process. Heavy-duty semi is not on internet time. It is on the time that you build steel mills, cement plants, and oil refineries. It is fabulously expensive, takes a vast quantity of planning, an immense amount of engineering work, and takes forever. We are very much in the middle of that. Do not hold your breath waiting for something you can play with. We would be delighted to have you help speed it up. Yes?
So what's the size of gold in millions of gates, not counting caches that you estimate?
I'm a software guy. You are asking the wrong guy, and I do not believe even the hardware guys, such as this gentleman over here, could give you even more than a wild-ass guess at this point. We have done some work on the hardware side, but primarily tool building, because I described earlier that everything is produced out of specs. And writing the tools that turn a spec into Verilog is something you spend a lot of time doing before you get any Verilog out at all. And
so the Verilog that you're getting is not yet synthesizable.
Hmm?
The Verilog that you're getting, you have not run through a
Oh, most certainly not.
No.
And it will be a while before that does. That's where the $8.5 million is going, among other things. We do have a standard comparison. We take the same piece of code and we'll run it on the Verilog when there is Verilog, and we'll run it on the SIM, and the two better produce the same, do the same thing. And the SIM is the definition of the architecture. Yes?
You mentioned a couple times in the talk that you were talking about modern architectures do this and modern architectures do that, and not talking about the mill, but explicitly not talking about x86.
Well, x86 is not a modern architecture.
So
I mean, it is a modern implementation, and an amazingly good implementation for a grossly antiquated architecture. I mean, the heroics the guys at Intel go through in order to make that sucker be able to compile and execute 4 instructions every cycle is extremely impressive. And I'm sure every one of them could do a much better job with a modern architecture, but they can sell what they got.
So what are some examples of modern architectures, and then corollary what makes them modern, but I'm more interested in the examples.
Well, the most recent fancy buzz for a new is RISC-V. RISC-V, Berkeley. I mean, that architecture, I mean, like it or not like it, or believe in RISC or don't believe in RISC, I'm not going to touch religious wars, but that architecture has been done in the last decade. There's not many that have been done in the last decade from scratch. That was done from scratch. We were done from scratch. Again, please?
How about ARM?
Well, ARM is peculiar in that they produce a new architecture about every 5 years. There's no such thing as an ARM architecture. There's about 6 of them at this point. And the new ones, ARM recently did a new extension in which they were able to do lane-based predication of vector operations. And I forget what the acronym of the name of this is, if anybody can help me. But it's a very fine piece of work for solving a tough problem. We also solve it. We solve it in a different way. But yes, that is modern, but that's essentially a piece of an architecture rather than a whole architecture. I mean, it's the fact that we do exit prediction rather than branch prediction, that's just a piece of the mill. There's a lot more to it, as you'll see if you wade through some of the videos. Yes?
Could you go back to the exit prediction?
Yes.
What was the rationale, or why after a certain number of exits you just don't even try to predict?
Mostly because we can't get a prediction back before we've already executed the thing. The mill is a fire hose. It is not stalling for anybody. As soon as we get the correct target, or the correct fall through, if it was the correct fall through, up, we're just decoding and executing, away we go. And the prediction, we're already probably past the point of prediction by the point that a replacement prediction would come in. The exits also are much bigger than a branch would be. A branch only has to report one bool, whereas we have to say where it is, where we're going. The exit actually is not all that much better than branch across the range of possibilities. But it offers us one immense advantage, and that is that we can predict what this execution will step through address by address by address without looking at the code. Branch prediction, well, you know at this address whether, if it has a branch, whether it will take it or not. But then you have to go and look at the next piece of code, find the next branch instruction, and figure out where. So it is not possible to chain ahead of it in advance. You have to actually look at the code, and that means that you have to fetch, look, fetch, look, fetch, look, fetch, look. Our exit prediction, and there's a whole talk about this called prediction on the videos. Our exit prediction, we have where we're going in the prediction. So I don't have to look at the code. Oh, I'm going to do that next, and when I go there, I know I'm going to go there next, and then when I'm going to do there next. So as soon as we mispredict, we're chaining down those predictions. Prefetch, 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 prefetch. That's where the big win is for exit prediction. It's that we can prefetch. And so long as the exit prediction performance on things like chains of ifs are competitive with branch prediction, we are a big win. In fact, it's slightly better for typical code. Okay? Yes, and back.
So sanity check. Like, the numbers in the slides were about like the silver, right?
That's a silver.
Except the number 3, right? It's 3 deep across the range, correct?
I'm not sure what you mean by 3 deep.
Like 3 pipelines or three phases?
3 phases. 3 phases is standard for all mill platforms.
Okay, yeah. And does that roughly correlate to read, modify, write, or?
You can think of it as being in some sense conceptually related. The first ones are all the ones that produce a value that they don't have to look at. The canonical example is a literal constant. I mean, load a literal, that's it. That can be done in the decoder. We don't have to get a value to do something to. The middle ones need a value and produce a value. And the last ones are the guys that consume values, but we don't have to pass their results to anybody else. They don't have a result. And this chains naturally, and it fits into the encoding device naturally. And there is a vast quantitative explanation of how it works and why available on that website. Folks, each one of those talks is an hour or more. We got a dozen talks. Feel free. But I can't do 12 hours worth of talks during a Ask Me Anything. Yes?
So, I was just going to ask/clarify. Also, I had noticed in that phasing thing that because of the way they all nested together, when you did all of the loaded constants of one instruction in the first phase, while you're doing all of the ALU ops, while you're doing all of the return and
yes.
branch ops, sort of by definition, none of those, like they're all using different units, so they can all coexist nicely.
Any given member has a population of slots, and each slot has a population of functional units. You can put one operation in each slot max. You don't have to fill the slot, but you can put one in each, the way you would with the VLIW. And if you don't have an operation of the kind that matches the functional units that are in that slot, you don't use that slot. It's that simple. That was the middle orange one didn't have any pure sources, and so that capability was not used in that instruction. It's the scheduler's job inside the compiler to maintain a pool of everybody that he could schedule and fit it in such a fashion that as best as he can, that a value is being produced immediately in front of the first guy who wants to use it. That scheduler internally is a Tableau scheduler, and this is a relatively standard thing that is used for wide issue machines such as VLIWs. It's more complicated for us because we have phasing and they don't, but the ability to, I have this, these are the kinds of things I could do, and these are the things that I want to do. What's the best way to pack them is it's a standard packing problem. You use heuristics because an optimal schedule is the bin packing problem, which is NP complete. Thank you, folks. Before we go, there's a postscript. You might have thought that doing that whole function in 3 instructions was kind of cool. Well, frankly, so did we. So we posted it up on the forum. Then the forum reader came up and hand wrote one that did the whole thing in 2 instructions. And there is his code. The compiler would not find this. As is always the case, a compiler's writer's job is never done. Here are the URLs for you. Have fun.